Okay, next we are going to discuss probability mass function, or PMF, for a scalar random variable x, which can take values in a finite set of possible values xi. In other words, it is a discrete valued random variable. We have its PMF, mu sub x at xi, the probability that x equal to xi, which is the value mu I, and there are, say, n such points. And these mu i's are called point masses. Now, similarly to the requirement that we had for a probability density function to integrate to unity, that's a proper PDF, we have the requirement for a proper PMF, being that the sum of those point masses equal to unity. Now, it's interesting how a PMF can be written in the same form as a PDF, even though one is discrete, the other one is for continuous random variable. Now, using the Dirac or impulse delta functions defined by delta of x equals 0 for every point x that is not 0, at every location where the argument is non-zero, the function is 0, but the function itself integrates to unity over the entire real line, namely it has a point mass, an impulse at the origin of area unity. With this, we can write a probability density function, a PDF, corresponding to our PMF as follows. P of x is sum of the point masses mu I, each multiplying a delta function located at x equal to xi, because the location of the delta function is where its argument equal to 0. So, with these impulse functions, we have a single way of writing a PDF and a PMF. Clearly, because each delta function integrates to unity, the integral of this entire sum is just the sum of mu I, therefore it is unity, so we have the normalization property satisfied in this case for the PDF, which really represents a PMF in our case. Now, the distribution corresponding to this density, more specifically the cumulative probability mass function, really that's the cumulative distribution. Now, the cumulative PMF is what we are looking at, would have jumps at those points where we have a delta function. It is a staircase function. Its derivative is 0 everywhere except at the jumps where it is an impulse function, and those are the delta functions, because the PDF is the derivative of the distribution function. The expression of the CPMF now can be written in terms of the unit step function 1 with argument, that's a symbol for a dummy argument, as follows. The probability of x less or equal to the number xi is the sum of the weights mu times the unit function with argument xi minus xi. These unit functions all start again at the location where its argument equal to 0, namely this one starts at xi equal to xi. That's where its jump takes place. Let's take an example, and this will be a Poisson PMF with what is called rate lambda. And this is a discrete valued random variable, the probability of x equal to n being e to the minus lambda t to the power n over n factorial, but here n really goes to infinity, so this is a discrete random variable, but it can take an infinite number of possible values. This describes the number of random points in an interval t, and I can also rewrite it now. Instead of the point masses here specified individually, I write it as a single PDF, a density. P of x equals sum n from 0 to infinity, there's all the possible values of n, and here we put the point masses e to the minus lambda t to the n over n factorial, multiplying a Dirac or impulse delta function with argument x minus n, namely located at x equal to n. Now, to make things a little bit more interesting, we can discuss mixed random variables, and they will be characterized by mixed probability PDF. A mixed random variable or a hybrid random variable x is one which can take values in a continuous set denoted by cap x as well as over a discrete set of points psi I. And again, for simplicity, we assume there's a finite number of such discrete values it can assume. Now, such a random variable will have a PDF of the form P of x is Pc of x, where Pc is the continuous part of the PDF, plus some mu I, these are the point masses, times the delta functions located at x equal to psi I for all the values of I. Clearly, the normalization requirement of this density is that it's integral from minus to plus infinity, which is the integral of Pc of x, and because it is defined on a set x, might be the whole line or part of it, doesn't matter, plus the sum of the point masses would have to be 1. So the total probability mass still has to be unity. Now we can have another mixed case where we talk about an event and a random variable. And in this case, we can define the joint probability density function of an event and a random variable as, and now using the full notation, cap p sub ax, arguments are a and psi being the value, will be the limit of the probability of the joint event that event A occurs, and the random variable psi is in this interval psi minus d psi to psi, and the whole thing divided by d psi. So really we take the derivative with respect to the random variable of this joint probability, and this for an event is just a probability, that's all. The simpler notation of this will be P of A and X, that's the joint probability PDF of the event A and random variable X. And here now we use that funny notation where the arguments define the function. The reason all these mixed cases are brought up is that some of the uncertainties in estimation problems are naturally modeled as mixed random variables. When you define what's called a hybrid system, which has continuous and discrete uncertainties, eventually we'll see this towards the end of the course in multiple model estimation techniques. We have some quantities which describe the system that are continuous, others which are discrete. The model is discrete and is a continuous valued, what's called base state random variable, as we'll see later. Now, expectation and moments, and we'll start with a scalar random variable, are as follows. The expected value of a scalar random variable, which is called its mean or average or first moment, is E of x, expected value of x, is the integral of all the possible value of x multiplied by its density times dx. And this is denoted in the concise manner by an x bar or x over bar. The nth moment is going to be the expected value of the nth power of x, and this is the integral x to the power n px dx. What you can see that this really, the mean is like a center of mass, because this is the location of the mass at x. You have a mass p of x, or density of mass. Within a short interval around that location you have a mass px dx. You just sum up the masses times the length, and this will give you where the center of the mass is. Now we can define what is called a central moment, and we'll start with the second central moment, also known more concisely as variance. The variance of x is the expected value of the square of the difference between x and its mean. So this is really the mean of the square, the mean of the square of the deviation of x from its mean. And this is integral x minus x bar squared px dx. This can be also seen as a moment of inertia, if you think in terms of mechanical terminology. Now, this, and I suggest that you go through this small derivation. If you open the parentheses, you will have really three terms that boil down to two terms that are shown here. The expected value of x squared, this is the second moment or second non-central moment, minus the square of the first moment. This is denoted concisely as sigma square sub x. The square root sigma or sigma sub x is called the standard deviation. So here is the variance, and sometimes we will denote to whom, to which random variable this belongs by using a subscript or sometimes without it. The random variable x, whose mean is x bar and variance is sigma square, will be denoted as x distributed with mean and variance, and we indicate those two values there. Now this is somewhat similar to what we have seen before in the Gaussian. You can say random variable x is Gaussian with that mean and that variance, except that now we don't specify the distribution, we just say it has these two moments. Now, the second moment, which is, as already mentioned a moment ago, the mean square value, or MS value, E of x squared, this is now the inverse of the relationship between the mean, the second moment, and the variance. So the mean of the square is the square of the mean plus the variance. X bar squared plus sigma x squared give you the second non-central moment. So you can see the non-central moment is the central moment, second in this case, plus the square of the mean. Now, for a zero mean random variable, the standard deviation is also the root mean square value. Because this mean is zero, this is the mean square value, the square root of this is the root mean square value. It's important not to confuse this with the root mean square value of a waveform, because here the mean is taken as a statistical average, an expected value, while in the RMS of a waveform the mean is taken as a time average, integral over a period divided by the length of the period. So while the terminology is really the same, the two have significantly different meanings. Some examples. Let's take a random variable x uniformly distributed in this finite interval AB, which we write that p of x equals the uniform distribution with argument x, and the two parameters are a and b, these are the ends of the interval, is 1 over b minus a as long as x is in this interval AB and 0 elsewhere. Clearly, if you integrate it over that interval, take the value, it's a constant, multiply by the length of the interval, you get 1. In this case, as far as moments are concerned, the mean of this will be the midpoint of that interval, b plus a over 2, and the variance is b minus a squared over 12. Again, these are small exercises. I would suggest that you go through if you are not familiar with this material. Now, for Gaussian random variable, take a Gaussian random variable with the two parameters mu and sigma square, again, mean and variance now. were the names we gave, but we did not justify yet, or did not have the justification. Now we will have the justification for the terminology already used earlier. E of x is the integral minus 2 plus infinity of x, and here's the PDF. That's a constant, the normalization constant, e to the minus x minus mu squared over 2 sigma squared dx. Now, what we do is we add and subtract mu to this x here. The one that has a mu subtracted will become the first integral, where we add, we pull out the mu because it's a constant outside the integral times the integral. Now, what does this integral give us? Unity. What does this integral give us? If we look at the density, it's a symmetric function about the origin, and x minus mu is anti-symmetric. It's an odd function. This is even. Therefore, the 2 halves will cancel. There's a requirement here which we know it is satisfied, but it's worth mentioning. You can cancel them if each of them is finite. You cannot cancel plus and minus infinity. That would not exist. So what we have is one term, first integral 0 due to symmetry, and this being anti-symmetric, this symmetric, and the second is unity due to the normalization property of the PDF. This integral has to be 1. Second term of interest will be the variance, ex minus mu squared. This is integral x minus mu squared, normalization constant, the exponential x minus mu squared over 2 sigma squared with a minus. And we can change the variable and still denote it by x, just shift to x minus mu equal to y, then take the y and designate it as an x, so we don't have a mu. So this is the expression of the variance. However, we cannot solve this integral directly, because this is an e to the minus x squared, and that does not have an antiderivative. So what we do is go back to the identity that we have, that the integral of the density is 1, and we shift the sigma from the left-hand side denominator, that's the denominator of the normalization constant, to the right-hand side. That's why sigma doesn't appear in the left-hand side, and there was a 1, and now it's multiplied by sigma. Now, this is an identity. So what we do is we will differentiate this with respect to sigma. That's a nice, convenient way of doing it. And once we differentiate, we end up with this result, that integral, and there will be a sigma to the power 3, because what we have here is was a 1 over sigma squared, that becomes a sigma to the minus 2, differentiate is sigma to the minus 3, and the exponential stays as is, so the differential of this is really x squared over sigma cube, and there's a minus that cancels with this minus, and the right hand side just gives us plain unity. And now you immediately see that take 2 sigmas, or a sigma square, from the denominator in the left hand side, put it to the right hand side, and you immediately end up with the expression of the variance as sigma squared. Therefore, what we have, this integral, is sigma squared, and this now proves and provides the justification of the term variance for sigma squared, which was originally defined without this justification in the Gaussian density. Next, we'll take a look at a Poisson random variable, and let's calculate its mean. This is a discrete a discrete valued random variable, and we write its PDF in the form with the delta functions multiplied by the probability masses here. So this integral x sum the masses times delta functions. Each delta function just gives a 1, so you pick up the masses would or at the locations x equal to n. And here is what we have. You look at this and immediately you see that summation is over n, This is an e to the minus lambda t, can be factored out, and an n cancels. We have one more lambda t here that can be pulled out, and the sum lambda t to the n minus 1 over n minus 1 factorial is exactly e to the lambda t. So that is the definition of the exponential. Therefore it cancels because that's e to the plus lambda t, there's an e to the minus lambda t, so we end up just with a single lambda t. Again, I suggest that you go through this algebraic manipulation. Now, what happens if we have two random variables? In this case, we can talk about the joint probability density function of two random variables. This joint PDF of x and y will be defined in terms of the probability of a joint event as follows. We will use the set intersection symbol or logical AND. This is the joint probability that x is in the small interval psi minus d psi to psi, y is in the small interval eta minus d eta to eta. We divide by d psi d eta the length of those intervals and go to the limit as both go to 0. Now, what this is the probability that my pair of random variables is in this rectangle divided by the area of the rectangle, which is the d psi d eta. Obviously, d psi and d eta don't have to be the same, even though the figure shows them equal, but these are both small quantities. And at the limit, they go simultaneously to 0. So this is the definition of the joint PDF, starting with the joint event. A small rectangle, a random variable x and y yield a point in the plane in that rectangle divided by the area. So that effectively becomes a second derivative, as you'll see. Integrating now the joint PDF of two random variables over one of the random variables will yield the PDF of the other random variable. Integral pxy, and we're using now the full notation. This is the PDF of the random variables x and y at location psi and eta over eta is px at location psi. Or the same thing could be rewritten using the simple density. Integral pxy dy is px, but now these two p's are definitely not the same. These are different functions defined by their arguments. This resulting PDF that pertains now to only x is also called a marginal PDF or a marginal density. So when you start with a joint, you can do what's called marginalization, and the origin of this term marginal is from statistics. They used to put a big table, and on the margins was x and y, and you sum up all the the values over y, you get the probability density function of x alone. And this can be easily seen by looking at the previous page. Here, what we want, if all you are interested in, say, psi between psi and psi plus d psi, you take all the possible values of y. So this is really an integral over y gives you, of the joint density, all the possible values. Y you don't care anymore, you just get the values, the probability that x is between psi and psi plus d psi. As a matter of fact, there's a slight discrepancy here. This is psi and psi minus d psi. Probably this could have been changed to an eta here and eta minus the eta, but it really doesn't matter. Now, another term, covariance and correlation coefficient, would be moments of two, or joint moments of two random variables. The covariance of two scalar random variables, x1 and x2, with means x1 bar and x2 bar, denoted as cov x1, x2, it will be the expected value of x1 minus x1 bar times x2 minus x2 bar. And this is the integral of this term x1 minus x1 bar times x2 minus x2 bar multiplied by the joint density of x1, x2, dx1, dx2, and the notation, this is not a very good notation, but we still use is sigma square x1, x2. The reason it's not a good notation is it is not necessarily positive. So even though it's a second moment, so this really square has to be interpreted in a slightly loose fashion, because as we'll see, you can have positive or negative values for this. Now, the correlation coefficient of these two random variables will be a normalized version of the covariance. Here's the covariance. Divide by the standard deviation of x1 and the standard deviation of x2. You will get really a dimensionless quantity, because the numerator is really the product of those two guys. And the denominator again has the dimension of the product. And this is rho 1, 2 for these two random variables. And what we have now is a result that the magnitude of the correlation coefficient of any two random variables obeys an inequality. The magnitude of rho 1, 2 is less or equal to 1. And this is really a counterpart or a consequence of the Schwartz inequality for random variables. Remember, when you have the inner product of two vectors in a plane, this is the product of the length times the cosine of the angle between them. Imagine this is same thing, the product of the lengths times the cosine. These are the lengths. This is the standard deviation. These will be the counterparts of the lengths. Therefore, what you end up is this is like a cosine. Therefore, in magnitude is within plus minus 1. Or its values are between plus minus 1. In magnitude is less or equal to 1. And we'll come back to discuss the inner product of two random variables, which is really the covariance, and the variance is a norm squared. Norm squared is like a length squared. The variance has the interpretation of this. The standard deviation has the interpretation of the norm, and the correlation coefficient that we have here is the ratio of inner product to the norms, to the product of the two norms. Okay. If we take two random variables whose correlation coefficient is 0, they are uncorrelated. This uncorrelatedness property of two random variables is equivalent to the fact that their covariance is 0. Two random variables, x1 and x2, are uncorrelated, it turns out, if and only if the expected value of the product is the product of their individual expected values. So E of x1 and x2, or the product x1, x2, is the same thing as E of x1 multiplied by E of x2. Now, there's another extreme. One was correlation coefficient 0, the other extreme would be the correlation coefficient is 1. Again, think of like cosine 0. The angle for cosine 0 is 90 degrees. In geometric context, those two vectors in the plane are perpendicular, orthogonal. And we'll see how this carries on over to the case of random variables. Now, what we have at the other extreme, unity. The cosine is 1. The angle is 0. They are one along the other. The two vectors in a plane which are at angle 0 with respect to each other point in the same direction. So 1 is really a linear multiplication, a constant, because the magnitudes have been cancelled. They point in the same direction. So 1 is linearly dependent, a linear function of the other. Now, two random variables, x1 and x2, are said to be linearly dependent if a1x1 plus a2x2 is 0, and we do have a pair of constants, these coefficients, a1 and a2, such that they are both non-zero. which means one is either a scaled version of the other one in its original direction or in the opposite direction. And this is the essence of linear dependence of two vectors or linear dependence of two random variables. Let's take an example. We'll take the random variables x and y. Their means will be x bar and y bar. Their variance is sigma x squared and sigma y squared. And let's assume they are uncorrelated from each other. Namely, the covariance of x and y is 0. And we'll look at the sum, z equal ax plus by with some constants a and b. And we will be evaluating the first two moments of the new random variable x, which is this linear combination of x and y. The mean z bar, that's e of z, is the expected value of ax plus by. Now, what is the expectation? It is an integral. A is a constant. We always like to pull out constants from any integral to make life easier. So we can pull out the a, and now we have expected value of x, but we know what is this. This is x bar. So z bar turns out to be ax bar, and similarly the second term will be plus by bar. The variance of z is defined as expected value of the square of z minus z bar. We substitute for z ax plus by. We just obtain the z bar as ax bar plus by bar, change the signs, subtracting here. Group the terms such that we can factor out a, so the expected value will be of the square of the sum of a times x minus x bar and b y minus y bar. Now we have two terms, and we open the square and pull out the constants outside the expectation, because that's an integral, and we have a square expected value of x minus x bar squared. We know what this is in a moment. We'll have the notation. You already see it here. A square sigma square x is a b square expected value y minus y bar squared. That's b square sigma y squared plus a cross term. Now we said that the cross term is 0, so we are finished. We have no more terms. So what we have now is the result that the variance of the linear combination of two random variables equals to a linear combination of their variances if they are uncorrelated from each other. Now, the covariance between z and x, e of z minus z bar, x minus x bar, where z now, as before, is ax plus b. We substitute the value here. We group the terms, because z is ax plus by, z bar is ax bar plus y bar with opposite sign. We factor out an a and b, and now what we have is expected value. Here's an x minus x bar, another x minus x bar, an a comes, this a comes out, and the result of the expectation is going to be sigma x squared, plus another term, which is b, again comes out from from inside the expectation operation, and we have the expected value y minus y bar, x minus x bar, which is the covariance of x and y, multiplied by b, but we said it's 0, so the result is just a sigma x squared. Now, there are very important concepts that some events and some random variables are independent. We say that two events are independent if the probability of their joint event will be the same as the product of their marginal or individual probabilities. Namely, the probability of A intersection with B, which is the same thing as probability of A, comma B, or A and B, equals to the product PA times PB. So this is the event A probability, this is the event B probability. Now, if you take a set of n events, AI, and such events, are called independent if the joint probability of the intersection is equal to the product of the corresponding marginal event probabilities. So the probability of the intersection I from 1 to n of all these AIs is the same as the product I going from 1 to n of the probabilities of each event AI. And there is another requirement that the same property should also hold for any subset of these events. In a manner completely similar to this, when it comes to a random variable, we can define n random variable as independent if their joint density, joint PDF, equals the product of the marginal densities. Namely, with a simple notation, no more subscripts p of x1 through xn, that's a joint PDF of n random variables, is the product of the n PDFs of all those pxi's, all the xi's, so the product of pxi. A set of random variables is called IID, that's independent, identically distributed. IID, if the property we have here holds and each marginal distribution or density is the same, which means each p of xi is the same function of the corresponding random variable. They are independent, which means when you have a random experiment, the realizations would be independent, but according to the same probabilistic law or probability density function or distribution. So that's important to understand that we're talking about belong to the same family of random variables, but they can still be independent because the mechanism of the experiment that generates them will be independent. Now, if we take the sum of two independent random variables, x1 and x2, and define this sum as y, it turns out that the PDF of such a sum is the convolution of their marginal densities. And now we have to use the notation here, P of y, there's a simple notation, that's the integral, P sub x1, this is the density belonging to x1, but evaluated at value y minus x, times the density of x2 evaluated at x, and integrated over all the possible values of x, that's integral from minus to plus infinity. This is the convolution, and this is the answer to the question, what is the density of the sum of two independent random variables? In most of our discussions, we will handle vector-valued random variables, and we want to know about how to characterize them, including their moments. First thing is the probability density function of a vector-valued or just a vector random variable, x written as a column, because that's a transposition of a row with elements x1 through xn, at location, at a point in the space, xi, with values or components xi1 through xin, is defined as the joint density of its components, P sub x1 through xn at xi1 through xin. What we're doing here is denoting this joint density as with the full notation with all components. Again, the full notation, but this is now a vector notation. The subscript is the vector x, the argument is the vector xi. This is the limit of the probability of the intersection of n events from I1 to n, that xi is between xi minus dxi and xi divided by the product of dxi1 through dxin. This is the element of volume or hypervolume in the n-dimensional space, and at the limit, as this volume goes to 0, we have the probability that this vector takes value in a small hyperparallelepiped divided by the volume of this parallelepiped. And we use the set intersection again, just to repeat the notation. A intersection B is the same as A and B is the same as A comma B. And we prefer the short notation P of X, and again you see now that X, we use the same notation for a scalar, the same notation for a vector, because we don't want to distinguish, and effectively every quantity we deal with is a vector unless stated explicitly that it is a scalar. So, and we'll continue using this unsubscripted notation where the argument of the function P really defines which function P we are talking about. If there is an ambiguity, we'll add subscripts to make sure to remove it. Now, moments. The mean of the vector x is the result of an n-fold integration. E of the vector x, integral, that's n integrals here, xi, that's a vector, p sub x at xi, dig psi 1 through dig psi n. So what we have is this n-dimensional n-fold integration written in one notation here, which is more complicated, and in the simplest possible notation on the other side of this equation. So again, n integrals xpx, product of dx1 through dxn, and the final simplest possible way of denoting the result is, as before, x bar or x over bar, and this is the mean of my vector x at this point. Now, we define the covariance between two scalar random variables, and now we'll define the covariance matrix of an n vector x, which we obtained from an n-fold integration. Again, now we stick to the short notation and we'll meet the limits of the integrals. So the covariance of the vector x will be the expected value of x minus x bar. This is a column vector. X minus x bar transpose is a row vector. So what we have now, a column times a row gives us a matrix, and will be a square matrix because they have the same dimension. So integral, again, this is really an n-fold but represented by 1, x minus x bar times x minus x bar transpose px dx. Now, this dx is again, with a slight abuse of notation, stands for the product of dxi. So this is the element of volume, and the final notation for the covariance will be a cap p sub xx. It belongs to x and it is x with itself, so the covariance, and sometimes we have a pxy, which will be the covariance between the vector x and the vector y. This is x with itself, and this is the reason for using the double subscript. The fact that we use a cap p here hopefully should not be confused with probabilities, because we use cap p for probabilities, but again, from the context it should be clear which is the meaning of it. So the result will be a symmetric n by n matrix. This is a dyad, and that's what causes the symmetry, and the diagonal elements of the covariance matrix are the variances of the components of x, while the off-diagonal elements are the scalar covariances between its components. One important property of the covariance matrix is that it is positive definite and therefore non-singular unless there is a linear dependence among the components of x. If there is such a dependence, then the covariance matrix is positive semi-definite, and obviously it is not going to be invertible, and this is one of the cases we are going to see in some real-world estimation problems. We can encounter such situations. The covariance matrices will be denoted by the symbol P, as mentioned before. with a subscript or argument in parentheses. The designation of a probability is P with braces. The argument is in braces for the event it pertains to, as shown in one of the previous equations. And with this, hopefully we will avoid any ambiguity.